Today I will talk about what's happened inside the Stirling engine and why the physical size and dimension of the Stirling engine matters. If you look at this small one, you can see on YouTube that the small one almost always run much faster than if you look at its big classic Stirling engine. And why is that? You can argue. I would say that depends on the contact surface to volume ratio in the Stirling engine, and that set the amount of heat you can push in the system per time. I'm in Stockholm and try to explain why it's an advantage to go isothermal and near discontinuous movements rather than sinusoidal movements and adiabatic Stirling engine. And I put a sketch here. The idea, if, for instance, this problem with pressure transient heat transfer losses is actually a losses you cannot get rid of in Stirling engines. So because of these losses, I would argue then that you want to extract all the area of the power before you move the displacer to another state. What's happened inside here, for instance, if you go down with the displacer, you move up the air and you have 100% regenerator. Let's say you cannot do better there. Then what's happened, you move up your displacer here, and the pressure increase everywhere equally in the whole chamber everywhere. And when you increase the pressure, the temperature also increase in all that gas molecule. So then you will actually push over heat energy to the cylinder walls when you have the gradient, the change in pressure when you rise the pressure, and then you may argue that right, if you have 100% regenerator, I could still run my engine near adiabatic, but because of these pressure transient heat transfer losses, you will lose the efficiency anyway. If you do not have these losses, then you could cut out a small part of the power and get good efficiency anyway. But I would say that when you move the displacer, then from there to there, you go down, or the opposite, you move the displacer another direction, so you cool down. Then you should extract every area you could have before you move the displacer in the other direction again. And that's why I think liquid piston Stirling engine is easier to build. This X value, you want that to be as high as possible to get the highest efficiency of your Stirling engine. The good thing is contact surface, you want that to be as high as possible, and the gas heat transfer, the speed you could push in the heat energy into the gas until it saturates to the cylinder walls. And the bad thing is volume, and the bad thing is frequency, who decrease this ratio. So that's if you look at for instance, my idea with the vessel here. You have your water surface, and you have a displacer here, and you have lots of plates submerged here. So in the upper part you have a classic near adiabatic behavior possibly, and here you have more like isothermal behavior. So at least at the cold part here, probably you could extract a lot of area. In the hot, then you maybe go more like that, I guess. But the nice thing with a water piston or a liquid piston stirling engine is actually you can build a very large piston. You do not have to mill out or cut out a very nice enormous power piston. You just have your liquid, and you can slow down instead you can slow down the frequency. You increase the volume, but you slow down the frequency. And I was inspired when I found out these materials, because then I could build my displacer very easy. It's like styrofoam. It's made of 100% recycled ordinary glass. So it's very light, like and very easy to shape. I want to shape it like this, the dome, and the upper part here I will weld a lid here with screws on, and it will, and similar will be on this part. This will be filled with water, will go up and out, and I will have my upside down underwater line ring boom driving rod for the displacer. So actually I look forward to make this finish this engine. Hope you enjoy my progress in an explanation in these topics. Have a nice day.